Hi everyone, this is Maverick Paul, the chemistry guru. Now for the last video lesson for 2021, we want to discuss something interesting involving Le Chatelier's principle. So let's take a look at this graph here. This is the concentration time graph involving the dissociation of nitrogen plus hydrogen to give me ammonia. And we know that this is a reversible system. This concentration time graph actually shows the change in the concentration of your reactants, nitrogen and your hydrogen, and the product, ammonia, as the reaction proceeds. And what we are interested in determining for today's video is what is the change that is imposed at time t that causes the subsequent change in the concentration of your reactants and products. In general, when we apply Le Chatelier's principle, we know that when a change is imposed to a system, the system will respond in a way to counter or oppose the change that we're imposing it. What we do is actually fairly simple. We just treat the system as a stubborn fella. Whatever you do to the system will not like it. You always try to oppose the change that you're imposing to the system. So in general, we have three changes that we consider in questions. First one is a change in the concentration of the reactant or product. The second one is the change in the total pressure of the system. The third one is a change in temperature. So these are the three main common changes that we will consider. Let us consider this part by part so that we can understand how would the concentration time graph look like when there's a change in the concentration of your reactant or your product. There's a change in the total pressure, as well as there's a change in the temperature. So let us consider each one of them part by part. Now the first consideration is the change in the concentration of your reactant or your product. So we know that according to Le Chatelier's principle, if you increase the concentration of the reactant, it actually doesn't like this change. You try to remove the reactant. If you increase the concentration of the product, the system doesn't like this product. You try to remove the product. So again, what you do to the system will not like it. So you always try to counter the change that you are putting into the system. So how would it translate when I try to put it into a concentration time graph? Then how would the graph look like? So let us have an example to illustrate this. Let's say I am increasing the concentration of your hydrogen. I'm increasing the concentration of your reactant at time t. Now, at the instance, at time t, when you're increasing the concentration of a hydrogen, so what we would expect is the concentration of your H2 will increase sharply. So this is what will happen at time t. Since I am increasing the concentration of a H2, so at time t, the concentration for a H2 will increase sharply, and at time t, there shouldn't be any sharp change in the concentration of your N2. There shouldn't be any change in the concentration of your ammonia. Only H2 concentration will shoot up at time t. Now, what happens next will be according to Le Chatelier's principle. Does the system like this increase in the concentration of H2? I know that when I'm increasing the concentration of your H2, according to Le Chatelier's principle, the system doesn't like this increase in the concentration of your hydrogen. So what you will do is the position of the equilibrium will shift towards the right hand side because it wants to remove this excess hydrogen, and therefore the position of the equilibrium will shift towards the right hand side. Now when the position of equilibrium shifts towards the right hand side, what you notice is you use up your reactant and you form your product. So the consequence involving that is this. Let me write this down here. The concentration of your reactant will decrease because the POE shifts towards the right hand side, favors the fall reaction, and the concentration of my product will increase. And this would mean that the amount of your N2 and H2 will drop, and the amount of your ammonia will increase. So when I try to go back to this graph and I try to reflect this in the graph, I know that the concentration for H2 shoots up, the position of equilibrium will shift towards the right hand side. You try to remove your H2, so the concentration for your H2 will decrease. This guy will come down. The curve will be something like this. This will come down and then it will stabilize. All right. How about my N2? N2, according to what we have talked about, the position of equilibrium shift towards the right hand side, the concentration for your reactant, N2, it is a reactant, it will also decrease. The N2 concentration will come down and it stabilizes, something like this, decreases, and it stabilizes. Now, involving the concentration for ammonia, the concentration should increase. So what we will expect is ammonia concentration will go up and it also will stabilize. All right, so the outcome of what this concentration time graph will look like should be something along this line. I will expect at time t, the concentration for hydrogen will shoot up. Then later the system will try to remove the hydrogen, the concentration for H2 will decrease, and the concentration for reactants in general will go down. So N2 concentration will go down. Ammonia, which is a product, the concentration will increase. It will gradually increase until it establishes a new equilibrium. Now, I think what is interesting and important is you notice when I increase the concentration of your H2 here to this certain amount, when the system tries to remove the hydrogen, it is not possible for the system to remove 100% of your hydrogen. I think this is important. You notice the increase for your hydrogen is so much. So when we try to draw the curve, and when you try to show the H2 gradually decreases, when this H2 reaches this new equilibrium, the concentration for your H2, when it establishes this new equilibrium, it must still be higher than the concentration of hydrogen in the original equilibrium. Because what the system can do is you try to remove the hydrogen, but it cannot remove it 100%. It can only remove part of the change in pose. I increase the amount of hydrogen by so much, I can only remove part of it. So we cannot draw this decrease in the concentration back to the same level. We cannot do that. I cannot draw the decrease in the concentration to below the original level. We also cannot do that. I think this is important when we are drawing this graph. When there's an increase in the concentration, then subsequently the system shifts to try to remove the excess hydrogen. Please keep in mind, I cannot remove 100% of your hydrogen. So the new equilibrium concentration of your hydrogen must still be higher than the original concentration of your hydrogen at the first equilibrium. Now next, how about the second consideration, a change in the total pressure? I know that according to Le Chatelier principle, if you increase the total pressure, the system will not like the change in pose. As mentioned, the system is a stubborn fella. Whatever you do to the system, it doesn't like, you always try to oppose you, correct? If you increase the pressure, it doesn't like this increase in the pressure, you try to lower the pressure. If you lower the pressure, it doesn't like this lowering of the pressure, you try to increase back the pressure. So how do we determine how the system will respond is we compare moles of gas on both sides of the equation. So let us put this in first. Involving my reactants, I have 1 nitrogen and 3 hydrogen. So my reactant, I'll have 4 moles of gas, 4 moles of gaseous species. The product, I will have 2 moles of ammonia. So I have 2 moles of gaseous species. And we notice that there's a difference in the number of moles of gaseous species. And when there's an increase in pressure, let us use an increase in pressure as an example. When there's an increase in the total pressure, usually how do we achieve that is I squeeze the volume of the container so that simultaneously there will be an increase in the partial pressure for your hydrogen, increase in the partial pressure for your N2, as well as ammonia. So the partial pressure for all the species will shoot up, and the system will recognize that you're increasing my partial pressure for all my species, and I don't like this increase in pressure. Now, increasing the partial pressure is equivalent to increasing the concentration, because if you reduce the volume, then you have a smaller space for all your species to swim around. So the concentration for your hydrogen will shoot up, the concentration for your N2 will increase, and the concentration for ammonia will increase at T. So what this means is, at time T, I would expect a very sharp increase in the concentration for your hydrogen, a sharp increase in the concentration for your N2, a sharp increase in the concentration for ammonia. So concentration for everybody increases. And this is when you are squeezing the container smaller, decreasing the volume of the container, so the total pressure increases, and the partial pressure for all my gases in the system will increase. And the next thing is to consider what will happen to the position of the equilibrium. Now remember, the system doesn't like this increase in the total pressure, so what you will do is it will try to lower the pressure, and it will do that by favoring the reaction that will form less moles of gas. What we do is we compare moles of gas on both sides of the reaction, and we consider in the for reaction, I will use up 4 moles of gas and I form 2 moles of gas. So there will be a net decrease in the number of mole of gas. So position of the equilibrium, if it favors the for reaction, there will be a decrease in the number of mole of gas, and therefore it will help to lower the pressure. Conversely, if you consider the reverse direction, if position of equilibrium shift towards the left hand side, then I'll use up 2 moles of gas, I form 4 moles of gas, there will be a net increase in the number of mole of gas, it will cause the pressure to go up. Since the system, in this case, wants to lower the pressure because you increase my pressure, I don't like this increase in concentration. I want to lower the concentration. So I'll favor the formation of less moles of gas. In this case, I would expect the position of equilibrium to again shift towards the right hand side. Favor the for reaction, form less moles of gas, lower the total pressure. This means that if I consider the concentration of my reactant versus my product, the concentration of my reactant again will decrease and the concentration of my product will increase because I'm favoring the for reaction. I'll form less reactants and I'll form more products. So we can now put it back to the graph. I would expect the concentration for your hydrogen and nitrogen to decrease. So I'll draw something like this. This guy decreases and then stabilizes. Involving N2 is the same, decreases, then after that it stabilizes. Involving ammonia, which is the product, the concentration is expected to go up. So this guy will increase, then after that it stabilizes. So if we're required to sketch out how this concentration time graph will change when you're increasing the pressure for the system, then we will expect the graph to look something like this. Now finally, involving the third change, how about a change in temperature? Now when there's a change in temperature, the system again doesn't like this change in temperature, so you always try to oppose this change that you're imposing to it. So what we consider is, for example, there's an increase in temperature. If there's an increase in temperature, again the system doesn't like this increase in temperature. So what you will do is you will favor the endothermic process, because the endothermic process will absorb heat from the surrounding, cause the temperature for the surrounding to decrease. In this case, when there's a change in temperature, what we will do is we will focus on the enthalpy change of the reaction. You notice this forward reaction from reactant to product, your delta H, it is a negative value, which means that the forward reaction is exothermic. That means the reverse reaction is endothermic. Forward reaction is exo, you give out heat, cause the temperature to increase. Reverse reaction is endo, cause the temperature to drop because it absorbs excess heat from the surrounding. Now what we want to consider is what happens at time t when you change the temperature. Now when you change the temperature at time t, let's say you increase the temperature, at time t there will not be any significant change in the concentration of your reactants and in the concentration of your product. So what the system or what the species will do is, when there's a change in temperature, the system will feel the change in temperature, then it will respond. So at time t, we do not expect any sharp change in the concentration of your reactants, in the concentration of your product, but later the system will respond, depending on whether it favors the exothermic reaction or endothermic reaction. So at time t, there's no sharp change, but the system will still do something about it when there's an increase in temperature. Now, as mentioned previously, the system doesn't like this increase in temperature. I want to lower the temperature by favoring the endothermic reaction. So if I look back at the equation here, forward reaction is exo, reverse reaction is endothermic. So what we will expect is the position of the equilibrium will shift towards the left hand side, favor the reverse reaction. Because the reaction is endothermic, you absorb heat from the surrounding, you cause the temperature to decrease. What we will expect is the concentration of my reactant will increase. I'm forming more reactant. The concentration of my product will decrease when the position of equilibrium is shifting towards the left hand side. I'll expect to form more reactants, I'll have less product. So if I try to put it back to this concentration time graph, how will the graph look like? I'm forming more reactants, so the concentration of your H2 will increase. then after that it stabilizes. Involving N2, it will also increase, then after that it stabilizes. Then involving ammonia, which is the product, the concentration will decrease, then after that it will stabilize. So we would expect the concentration time graph, if there's a increase in temperature, the concentration time graph for this system will look something like this. I think what is important is we need to be able to deduce the changes in pulse based on what happens at time equals to t. Alright, so maybe let us run this through and we recap the few examples that we've talked about. So involving scenario number 1, when there's a change in concentration of a reactant and product, what happens when you look at time equals to t is there's only one sharp change involving one of the species, either the reactant or the product. In this case, the concentration of your hydrogen increases sharply, but the concentration of the rest of the term at t doesn't change. Then later the system will respond. So when we encounter a graph like this, when there's only one sharp change in the concentration of a species, sharp increase or sharp decrease, then we know that what we are doing is we are either adding that species or removing that species. I'm changing the concentration of one particular component. So this will be changing the concentration of the reactant or the product. Then we will decide how the system will respond accordingly. Now involving the second change, what happens when there's a change in the total pressure? When there's a change in the total pressure by changing the volume of the container, the concentration for the reactants and the product, everybody will be affected very quickly. So we will expect a very sharp change in the concentration for all the species. All the species concentration will increase when you're increasing the pressure. All the concentration will decrease when you are decreasing the pressure. So when the concentration for all species change sharply, then we know that this is because of a change in the total pressure by changing the volume of the container. Then finally, when I consider change in temperature for the third scenario, changing the temperature at T, there's no sharp change in the concentration of the species, but later the system will still respond. So when we see a graph which is something like this, at time T, there's no sharp change. We know that this is due to a change in temperature. Alright, so finally we can come back to this question. What is the change in pulse at T? Back to this graph that we have here. Now, when we consider this graph, the focus is on what happens at T, correct? You notice there's no sharp change in the concentration for your reactants and in the product. This will mean that it must be a change in temperature, either an increase in temperature or a decrease in temperature. The next thing we do is we consider, okay, how did the system respond? Does the position of equilibrium shift towards the left-hand side or right-hand side? So we do this by considering what will happen to the concentration of the reactant and what happens to the concentration of the product. You notice what we have is the concentration of your reactant, H2 and N2, increases. So I will have more reactants, forming more reactants, and the concentration of your ammonia decreases, so the concentration of your product decreases. If I'm forming more reactants and less product, it will mean that the position of the equilibrium is shifting towards the left-hand side. POE actually shifts left, favors the reverse reaction. And since I know that this change in pulse is a change in temperature, what I can do is I can focus on the enthalpy change of the reaction. For reaction is exo, reverse reaction is endothermic. So since the position of the equilibrium is shifting towards the left and the reverse reaction is endothermic, the system is actually favoring the endothermic reaction. And we know that endothermic reaction is absorbing excess heat. And since the system will respond in a way to counter the change in pulse, if the system is favoring the endothermic reaction to absorb my excess heat, this will mean that the change in pulse at time equals to T must be an increase in temperature. Now, some of us might find this a little bit confusing because what we are doing is we are working backwards. Based on the outcome, I work backwards and I try to deduce the change in pulse. If it is confusing for you, it's actually quite simple. What we can do is, first thing is we recognize that at time T, there's no sharp change, so it must be change in temperature, either an increase in temperature or a decrease in temperature. So there are only two possibilities. Temperature go up, temperature decreases. Then the next thing we can do is we can consider, okay, what if there's an increase in temperature? So we will think of it in the forward direction. When there's an increase in temperature, the system doesn't like this increase in temperature, favor endothermic reaction. So based on this reaction, forward reaction is exo, reverse reaction is endo. So POE shifts left, form more reactant, form less product. Then you look back at the graph, you notice it is consistent. The amount of the reactant goes up, the amount of the product decreases. So this will mean that the change in pose is an increase in temperature. So if you are thinking that if it is an increase in temperature, then you do all this rationalizing and we have a conclusion involving what will happen to the position of the equilibrium and what will happen to the concentration of the reactant and the product. Then when you look back at the graph, then you realize that it is not consistent, it is different. So it will not be an increase in temperature, it must be the other way around, it must be a decrease in temperature. So some of us might find this a little bit confusing because usually we don't do it in this way. Usually we don't have the outcome and we deduce what is a change in pose. We're more comfortable with, you give me the change in pose, I tell you what will happen. We're more comfortable with that. So what we can do is we can consider, is it an increase in temperature or is it a decrease in temperature? Because there are only two possibilities, correct? If it is not increase in temperature, then it must be the other way around. We have talked about quite comprehensively what would the concentration time graph look like when there's a change in temperature, when there is a change in the concentration of the reactant and the product, and also when there's a change in total pressure. Focus is on time t. What happens? Is there any sharp change in the concentration of the reactants or the product? And from there, we are able to decide what is the change in pose. Alright, so that was the discussion involving Le Chatelier's principle and the concentration time graph. So if you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. Now we will take a 2-week break for our Christmas holidays and New Year. So we will come back in 2022. So have great holidays and I'll see you next year.